Hello to viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're gonna talk about NASA's SPHEREx. So let's dive deep into it. Now this is SPHEREx. So it is spectrophotometry for the history of the universe, epoch of reionization and ice explorer. Do not ask me what they were thinking when they named it. It's like I think they wanted it to call sphere and then they are like, ouch. They just forced something into it. It has literally has three adjectives inside it. It's like history of the universe, epoch of reionization, and ice exploration. Three things are there in the name. I'm like, relax, man. Uh, so proposal of this puppy was submitted to NASA in 19 December 2014, so to say. Now, here's the deal. This is a common thing. NASA gets a lot of proposal and majority of them they reject. But just because they reject it does not mean that project is thrown out. It's just like sometimes they come back with vengeance. And sometimes they get approved for different mission category and all that. So it's a common thing. So you were like, hey, you asked for it in 2014 and you got approval in 2019. Yeah, it's normal. It's surprisingly normal. So NASA approved it. Now NASA earlier the team that was designing this, they wanted it for small mission, but NASA yeeted that out of it. So they went for the broke part and they went for medium class exploration mission. Now thankfully they found it wise to be in that economical category, because this category has limit of $250 million cap, meaning your craft itself should not cross this. And this sort of missions are low priority, meaning if you cross it, they will cut it. So this is not something where it's like James Webb Telescope, oh, it's supposed to be done in 1 billion and it's going to keep eating money. No, this is like, oh, you over budget, bye. So fundamentally speaking, this is a different kind of work ethic when you are dealing with this sort of mission. And NASA has learned a lot of lesson getting trolled by James Webb Telescope. That is like, no, this is how we're going to do it. This is how we keep our losses to minimal. And it has worked so far very well. There are many missions. Generally, they do one or two every few years. So it's working out quite far, and the planned launch is April 2025. So that's time they're supposed to be using SpaceX Falcon 9, which at this point, do we even see any other rocket at 98.8 million? I'm like, to just round it up to 100 million. So I do expect this puppy to cross around $500 million when it's completely done. Like the ground crew cost, of course, they are not hiding that. This is just the craft. This is just the rocket. The ground crew is the expensive puppy. So we do expect like full mission. But if it completes under $500 million, that's like shut up, take money. That's good. So what are they going to do? Okay, they had a mission. What the hell the mission is going to do? Mission is near infrared. Okay, so we have infrared. Infrared is a wide band, like huge band. Like if you think optical is huge, nah man, infrared huge. So this band is so huge that to make sense of it, we divided it in multiple sections. So we have short, medium, long. And long is very hard. Even James Webb Telescope does not do it. It only goes to medium or short. This puppy is short and medium. So near infrared, it's going to do that. And it's going to do all sky survey. That's the essence. It's James Webb Telescope is like a sniper. So you look at it, it's like, bro, I got this. Awesome. But here's the deal. What about here? Has no idea. So if you have seen any movie where they have, depict snipers properly, sniper is there. There's always a person next to him, which you call spotter. This sort of mission is what we call spotter missions, where the data that's going to come from this puppy, that's awesome. On its own, that's like shut up, take money. But this data, if they find something, whoa, what is happening here? What is happening in this galaxy cluster? What is happening here? Then they can ask some big puppies like James Webb Telescope to, hey, look into this direction, so to say. So that all sky survey with this infrared spectrum, shut up, take money. So they have 3 mirror design and they have a diacritic beam splitter, so they can have 6. It's a small puppy. The telescope itself is physically small. That's why they can even fit inside it. And yes, it's being built. It's not like, oh, it's just on paper. No, it's being built. Majority of things are still built. The only thing I think has still to be built is the bus. The telescope is almost completely done. It's on testing right now. It's just the bus as in the data communication and star trackers and all that. So what's the aim of this puppy? You do not go to, it's like, okay, I'm going to do this. Like, what is your aim? So aim is first all sky, let that be clear. Full sphere of basically planet Earth should be captured. Full sphere. All sky, near infrared spectroscopy. People lost their stuff there. Spectroscopy. It's not giving you a photo in infrared. It's telling you the spectral graph of it. And that's hard to do. Spectrograph requires you to take a light, split it through a prism, and then study all of it. Now, here's the deal. If you think about it, okay, that means my giant basically sensor fundamentally becomes a very limited sensor. It's like, yeah, I have a huge sensor, but the moment you put a prism in front of lens, all you're gonna get is spectrum. But you no longer have resolution, or your resolution literally went from 2 dimensions of resolution to just 1 dimension. So how the heck you gonna scan whole sky? How the heck you gonna have that spectroscopy of the whole sphere? That's the expensive part. To do this in other system, for example, James Webb Telescope, it has moving things, lot of moving things. It has micro shutters, it has filter wheels. So how and be mindful, moving things in space observatory equals, don't talk about cost. Like, it requires blank check to do. So how the heck this tiny telescope, you can see, it's a tiny puppy. How the heck they're gonna do that? Like, how? So I will discuss about that. So that's why the moment they said near infrared, that's okay, that's good. Spectroscopy, whoa, all sky, done. Shut up, take money. So their aim is, like, again, because you have such a wide view, you do not have the deep view. You will only see 300 million galaxies and 100 million stars that is in our own Milky Way. So while you are seeing a lot of it, your lens is wide, you do suffer the depth of it. So you do not have the depth of JWST, but still good enough. Let's just say 300 million is like very good. 300 million is good. Now what it will explain, like, the data came in, what that data should show. That data should help us to understand inflationary birth of universe. So we had Big Bang, okay, we got it, awesome. What happened after that? We have no idea. So this also should allow, because of such a wide field, because of the whole celestial sphere, it should allow us a data context where we can rewind the clock. Okay, this is how galaxical structures were made. This is how superclusters were made. Like, there are many things that we see. There are patterns, there is signatures there, where it's like, okay, this trendle is there, this lot of galaxy here, there is a void space here. So this, the fact that it's scanning everything in infrared and is scanning the whole sphere, it should allow much higher resolution, which will help us to understand how that mathematics happened. And large scale stuff, basically that galactic stuff, where, because there are places where like lot of galaxies, other places, nope. How? So that will help that. Formation of early galaxies, because we had stuff like elements. Elements got together, they got boom, they got married, and they got divorced. We call it fusion. And once they had that, we had a lot of energy. Okay. So from stars to heavy material, heavy elements to galaxy, that's a jump. Like, how the heck that jump happened, where we went from stars ignition to full-fledged galaxy structures. This will also help in that, and it will also help in other tools. So if it spots something that's like, whoa, something unique is happening here, other telescopes that are more powerful will be like, I get this. So that's there. And then we come to the third part of it. When did water started to happen? Water is basically marriage of oxygen and hydrogen. We know hydrogen came very early. That's a known thing. When did oxygen came? When did specifically oxygen started to make love with hydrogen? When did that happen? When they started to make their family. Basically, they started to clump together, become things, ice. They started to become a component of a celestial body. When did that happen? So this will help in that. That's why we need full sphere. We need to see what's happening all around us in infrared. So even those signatures that's supposed to be in visible light, because of the distance from Big Bang, temporal distance, that is like, billions of years, it would have stretched into infrared. This puppy will see it. So when did water happen in early galaxies? And again, IR itself will help in all of those. Spectroscopy, done. Spectroscopy is giving you signature. Basically, every pixel, it's covering every pixel. Basically, thing in this design, I will explain how far they are doing. It's fantastic, mind-boggling. It's like every pixel, it can just see one spectrum. Every pixel in a sensor, giant sensor, can see only one spectrum. So let's understand the telescope part of it. This is the magic, which is like, it took me time to understand. This is mind-bogglingly amazing. Basically, every pixel that you have can only see in one spectrum. That's it. Like, if you have like, let's say 100 nanometer, let's just go with that number. Only one pixel will see. The pixel next to it will be 102 nanometer pixel. After that will be 104 nanometer pixel. After that will be 100. It's like, how the heck? Let's dive deep into it. So effective aperture of this telescope is 20 centimeter. So you get that point. It's like many amateurs have bigger than this. So it's like, it's not big. However, each sensor itself is seeing around 3.5 degrees of space. So that translates to around this. Like, do this into the sky, that's how much area you're seeing. So moon will look like, small area in the sensor. So you are looking at around, give or take, like a 300 millimeter on a full frame lens camera kind of thing, in that sort of ballpark. So you can see each sensor is square block, so that is 3.5 degree, and they have 3 of these in a 2 parallel rows, so you have 3.5 degrees multiplied by 11.3 degrees. So field of view is huge. The telescope is not huge. The field of view is bonkersly huge. It's like, dude, huge. Now, it has 3 shortwave system. Again, these are shortwave ones, 3 long wave. These are long wave ones. And the sensor itself is square sensor. It's not like what we have in our cinema industry or cameras, which is rectangular. This is 1 by 1. God damn it, square. So this square is 1 by 1, and it's 2K sensor. What does 2K mean here? 2048. Exactly 2084 pixel multiplied by 2048 pixel. Who makes this sensor? There is only one company. Most of the time I'm seeing their sensor only, which is Teledyne Imaginations. Teledyne Imaging Sensors, Hawaii 2RG. Type this name and you will find the exact sensor used. Now be mindful, the sensor is a category. You have to call up them and tell them it's like, we want in this spectrum. They will fine tune the final structure for you. So they have that. Now so far, well, okay, so far it's normal. To make sure they have this 11.3 degrees of field of view, they have to do something clever. So what they did is, the telescope is small. So what if, like, hey, what if we have telescope, but we put a beam splitter in the middle of the light path? Now the same light field can go into 2 sensors. So 1 sensor, 2 sensors. So that's why this is the sensor block. 3 sensors are acting as 1 block. So you have 2 blocks. So they have diacritic beam splitter. So beam splitter allows basically looking like this, and all are coming from 45-degree angle. So that works. That's awesome. Now so far everything is normal. The moment they did the clever part, that's linear variable filter, LVF. This is the special sauce. So far everything is normal. Oh, do you have a telescope? Okay, everybody does. Do you have a sensor? Again, this very sensor is used in many things. So how the heck they are going from that to, like, we're gonna give you a spectra of every damn thing, which, mind you, it's very hard to do even for James Webb telescope. It has a micro shutter array. So how the heck they achieved it? And be mindful, to make sure the price is low, they have no moving parts. So they do not have filter wheel. How the heck they did it? Linear variable filter. It broke my brain, like, to understand how the heck they did it. That's why I said every pixel is only looking at one freaking band, nothing else, just one goddamn band. So this sort of filter is there, aligned on top of them, sliced into it, so it's perfectly aligned. So when you are scanning, right, imagine it this way. It's a LiDAR, like how you see LiDAR spinning. Think of it this way. From its vantage point, everything is spinning. So everything, every dot in sky will cross through all of them. Now here's the benefit. Everything is gonna cross through it. What's the point of just capturing one detail on it? Oh, it's how bright it is, right? If you do, and even color information is not that helpful. But if you put a linear variable filter, basically, which is acting as a band pass filter, every pixel can only accept it if it's at the right wavelength to pass through it. Meaning, it's like, hey, I'm only gonna glow if I'm 103. I'm only gonna go glow if I'm 105. I'm only gonna glow if I'm 106. Like, you get the part. Bands each have bands. So if one thing is going through whole of these sensors again and again, you're gonna get perfect signature of every celestial star point, all of it. So that's how they are achieving spectra. They are not just achieving, oh, photo. They are like, bro, this star, this is its spectral signature, because we scanned it on whole of these sensors, 6 sensors multiple times. Is like, details, sir. That's what the clever part is. The fact that they used a linear variable filter in this sort of arrangement, I was like, damn. Like, sometimes you see something like this, it's like, damn. So this is like, they are basically, every camera is 2D. This camera just went 3D. So we are like, we have X and Y, and we have third dimension of your spectrum. Like, damn. So this is the telescope part of it. Now, so far I'm talking about infrared. You must understand infrared means you have to be cool, because if you are not cool, you yourself are emitting infrared photons. So that's the issue. So JWST solved it by going to L2 Lagrange point, basically, which is behind, basically, if sun is the center, behind sun is basically Earth. You are in Earth shadow. You still getting some light. That's how your solar panels are working, but you're not getting majority of. Basically, sun's main oomph is blocked by Earth itself. And Earth is big enough where it's like sun's, if sun is dumping, let's say, 10 megawatts of energy, Earth is like, bro, no. Like, in my shadow, it will be freezing cold. So that's how they get to keep their equipments almost to absolute zero. So this puppy does not have that luxury. And given the fact that it's in low Earth orbit, you have to understand, low Earth orbit is hot. That's why basically ISS is white. It's hot, like it's getting cooked from Earth itself. Because think in this way, what happens during daytime? Sun dumps energy. What happens during nighttime? Earth dumps that energy back into the space. That's why we are not melting as of now. If global warming runs away, that's a different thing. But as of now, majority of that energy is being dumped away. And imagine what will happen to you, something that is orbiting. Yeah, you will be cooked from Earth itself, not the sun, Earth itself. So if you are doing something sensitive and you are in basically side of the Earth, that is like Earth is here next to you, like, only 100 kilometers. Yeah, you have a giant heating element below you. So that's the issue. And if you ever have sensitive instrument and directly looked at the sun, yeah, no, you will be deep fried. The end. So heat is a big issue. So they introduced a technology known as bucket or V-groove passive cryogenic radiators for shielding. The same technology is used for JWST. So what we used to understand is that we have a shield. Awesome. Now shield will reflect, let's say 90%. Okay. So what happens to that 10%? This heats up. Okay, what happens to that heat energy? It heats up, then it starts to radiate that energy. So basically the first layer gets affected by 300 Kelvin heat. Boom, it heats up. It starts to emit photon to keep itself at equilibrium. Okay, majority energy is rejected. That's awesome. But some still pass through. So that pass through starts to bounce around. If you have a second layer, it will bounce around them. Now here's the deal. Every time photon is bouncing, you have some probability of it being absorbed and some probability of it being reflected. So this planar will heat up a little bit, but not too much. It will heat up a little. But then again, you will not reach the temperature that you desire. So you put one more. It's still not. You have to put a lot of layers before you reach a point where it's like, no, now I'm perfectly cool. Now somebody figured out that there is an issue here. If you have two parallel plates that are reflecting photons, photons most of the time is going to be absorbed rather than being coupled from the outside, coupled as in like the photons going to the vacuum of space. It's not going to happen. So photons are just basically becoming a coupling device. So efficiency is very low. But what if you have this geometry, V shape? So benefit of V shape is that this angle, this geometry allows few bounces to photon to yeet out of there. Basically photons only need to bounce 3 or 4 times and it's just going to be out there. And if you have something that is only reflective, let's say 90% of the time, 2-3 layers, done. And if you have something that is 99.99% reflective on the spectrum that you worry about, it's like 1 or 2 layer, you will reach almost absolute zero. That's why V-groove is used for basically all space telescope, including JWST. And this puppy has basically 3 buckets. Now it's because it's getting cooked by everything, Earth and Sun itself. So it does have a thicker buckets. And this was their older design. I think this design was, they were targeting for lower cost at the small scale observatory, but now they have the cone. Bucket is much more thick. Now benefit, very good reflective, very more resilient, more able to withstand very thermal high flux. But again, it will heat up. It will reflect photons. Photons have to go to second bucket. Second bucket is like V-groove, bro, out. Then some amount will penetrate through. Third bucket. Third bucket is like, bro, no. First bucket alone removes majority of it. Second bucket, whatever remains. Third is just a buffer. So you have 3 buckets. 1 bucket, 2 bucket, 3 bucket. So this V-groove allows them to cool down. How cool down? Well, everything is passively cooled. It does not have a Stirling cooler that allows it to go even up closer, but it should be able to easily reach minus 210 degrees Celsius. And here's the interesting part. They don't actually need it to be this cool. They are cool for clarity's sake. They're not cool for instrument sake. The instruments are like, okay. It's not like we have to be cool or we're gonna fry ourselves. It's not that. It's like, oh, okay, you have minus 210. That's awesome. So passively cooled. It does not have radiators or radiator as in like it does not have Stirling cooler. So it can, if let's say missions works and instrument just keeps working, NASA will keep using it for years. It does not have inherent expiry date like JWST. So everything is passively cooled to minus 210 degrees Celsius and no moving part. The only thing it has like the shield that has to deploy and the cover for the telescope. So that's how they're keeping the cost low. And that's why even the base of the bucket is so shiny. Basically it's one bucket floating in the bucket with another bucket, and then you have a telescope in that bucket. So 3 buckets to shield you to reach a point of V group, and the temperature minus 210 degrees Celsius. So let's dive deeper into this. Now here's the, it will take around 30 days to cool. Again, that's the planning mission data that I'm looking into. That's what they are planning, that 30 days. It should be cool before that, but 30 days like damn sure. Now, it should be able to do, mission duration is 25 years. That's how much time they have asked from NASA. And they should be able to do 4 complete sky coverage, meaning 4 times they would have taken a complete snapshot, meaning one spot in sky itself should have been captured 4 times in all spectrum. Every single pixel should have gone there 4 times. So you should have a very high resolution photo of that. Now, how the heck you gonna dump that kind of data? Well, it has a Ka band antenna, which is 26 gigahertz. So that puppy should allow you around 10 Gbps of data. And since in low Earth orbit, it does have communication. And then it has S band, which I think is for telemetry or for backup, 2.2 gigahertz to 4 gigahertz. Now, it will start and stop a lot. So that's the one thing, because it's not a linear sensor. It's a full 2D pixel array. It does need to stop. So basically, it's moving. If it's not doing anything, it will go like this. It will remain at a fixed, basically it's moving in the orbit, so your field of view will move according to it, but it needs to fight it. Basically, look at this. It goes there, goes there, goes there, goes there, completes the photo, completes the photo, completes the photo. Bye-bye. It has to go down. It has to do like. It has to keep that. That's in the orbit diagrams. You can see this like. There are small movements, which they call basically small skews, and they have large slews. So small slews is like they're just moving from one band to another band, and large skews is like, okay, field of view is complete, now next field of view. So they have to do that. It will require a bit of tedious doing, but they have done this. Like this sort of approach has been taken by other spacecraft in space and have been proven awesome. So it's a known thing. It's not a new thing. It's a known thing. Now, they have a sun synchronous orbit, which is a very clever way of making sure that it never faces the sun, and sun is the one responsible for spinning it around the globe, around the orbit, so to say. So you are the sun, it's going like this. It's never gonna go like this. So the sensor will never ever be on your side. So it's always going like this. So brick by brick, day by day, it will keep going around you. So it will capture the whole celestial sphere. Now, orbit is 90 minutes. That's why I said every pixel is going to go through every single spot in the sky. So 90 minutes is going to do multiple times in one system. And if you want to understand what is the pixel resolution, that is 6 arc-second per pixel. It's not very high resolution, but for what it's providing, given the fact that it's providing a spectral photograph at 6 arc-second resolution, people like shut up, take money. So it's very good. Now, what about the exposure? What is the exposure length? That is 120 second to 150 second. That's what I'm getting at best time. So that is the exposure time. And because of the way orbits are done, polar regions is going to get precise detail. Polar regions, we're going to be like, damn. They're going to have like multiple paths, multiple angles. Polar points, basically faces going upwards and downwards. From Earth's pole point of view, we're like, we know. What are you? We can see things. So that's the detailed part of it. And you can see that it's like each slice is getting piled up, and then you are compressing all of the pile eventually. So like tick, 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 tick. And each of them in different wavelengths. So not only you are just getting a photo, you're getting wavelength specific information. It's like, if this is glowing, this is exactly which wavelength it is. So it's a really amazing thing. And they achieved it with surprisingly low moving parts, surprisingly less sensor count. I would have thought that they would have required like multiple sensors with multiple beam splitters. They're like, dude, one beam splitter, one linear gradient filter, done, go home. So it's very clever. So this was my presentation on NASA SPHEREx. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.